Chapter 3. Fluid Dynamics. A fluid supports no shear at rest. Fluids include air, water, thixotropic gels, and amorphous solids. The approach taken involves physics, thermodynamics, mathematics, and engineering, everything but religion, and even that if necessary. Fluids are sometimes described as a scalar field, if static, or as a vector field, with integrable flow lines. There is interplay between the mechanical energy of fluid flow, thus an elaboration on what is known from classical mechanics, and the energy associated with the thermodynamic state of the fluid. So we encounter a thermodynamic component to the theory that is foundational at the outset. Thus, fluid flow has two phenomenologies. 1. Classical mechanics with vector calculus. 2. Thermodynamics, using any pair of canonical variables, starting with standard density and pressure. From the classical mechanical, we have the velocity field of the fluid, 3 components in 3D. From the thermodynamics, we have pressure and density. Later, any 2 thermodynamics variable will suffice with known equation of state. So, as much as multi-element and continuum formalisms have been deferred, such as statistical mechanics and thermodynamics, there is some minimal discussion of such needed at this juncture. But first, let's eliminate the complexity of multi-element by continuum limit with a discussion of Loschmidt's number, leaving an approximate continuum, thus a pure thermodynamic formalism in what follows.
Loschmidt's number indicates how many gas molecules are present in a cubic centimeter at the Earth's surface, standard temperature and pressure. See equation 3-1. Even in a molecular-sized box of 500 nanometers on a side, we have roughly 3,000 molecules. Clearly there is a typically lot of intermolecular interaction, and thus rapid equilibration. Not so for rarefied gases, a topic not discussed in what follows. 3.1 Simple fluid dynamics, non-viscous, non-compressible, non-relativistic. In what follows, a fluid is described, seemingly, at a point, but this is actually taken to be a very small, almost infinitesimal, volume. Recall a cm cube has 10 to the 19th power molecules, so we can go considerably smaller and still have law of large number effects on the large number of molecules remaining. In this section, the notation of Landau and Lifshitz is adopted from their series book on fluid mechanics, and numerous problems are considered and solved from gas dynamics by Roshko and Liepmann and other sources. 3.1.1 Continuity equation. Following the notation of LNL, consider a volume V sub 0, with fluid density ρ, we can write.
See equation 3-2. And the exchange of mass at the surface is. See equation 3-3, where V is the velocity vector field of the fluid, and ρ density as before, and dF is a surface area oriented with outward normal. This convention then determines the sign conventions in what follows. Suppose, for example, that we have a decrease in the mass given by. See equation 3-3.
From the surface exchange, assuming no creation or annihilation of mass inside the volume. See the next equation. Thus, see the next equation. And we get the continuity equation. See equation 3-4. 3.1.2 Euler's equation. So far we have considered surface flux of mass density, ρV. What of the other vectorial thermodynamic variable pressure? In examining this, we arrive at Euler's equation, 1755. Start with the total force acting on the volume element. See equation 3-5. The element of force negative nabla bullet P indicated is acting according to the Newtonian F equals ma, where a volume element dV has mass density ρ, and it equals dV over dt, thus.
See equation 3-6. There is a subtlety in this analysis regarding the differential notation. The dV divided by dt referenced above is not the standard derivative on timeshift alone. See equation 3-7.
Thus, see equation 3-8. This is known as the Eulerian derivative, where there is not only a time shift on a streamline, but also a positional shift according to flow velocity vector field v. Accordingly, the Eulerian derivative for a vector field W is. See equation 3-9. And for a scalar is. See equation 3-10. Thus, see the next equation. Or, See equation 3-11.
If the fluid is in the Earth's gravitational field at the surface, we get the extra force rho vector g, where the absolute value of g goes to equals g, the acceleration due to gravity at the surface, directed downwards. See equation 3-12.
We will examine this last equation in the section on hydrostatics that follows. A note on ordinary differential equations and generalized derivatives. The central role of ODEs in many physics descriptions has been described previously, and in Book 1, and an extensive appendix of introductory and advanced ODE examples/solutions is given in the appendices of Book 1, Introductory ODEs, and this book, with Appendix D on advanced ODEs. We have now seen two forms of derivative variance. One was in the context of complex functions in Chapter 2, where a well-defined derivative was obtained by adopting the derivative being the same at a point in the complex plane independent of direction of approach in the limit process. This generalization to the derivative for complex functions had many ramifications. Now we are seeing a new derivative function with reference to a vector, flow, field according to Euler. The rest of this chapter will explore many of the ramifications of the Eulerian derivative. Looking ahead, however, it is natural to ask how such derivative generalizations will develop. Here is a list of derivative generalizations that will be considered, before arriving at quantum field theory descriptions, where spinorial fermionic variables are needed as well.
1. Complex derivative, Chapter 2. 2. Eulerian derivative, Chapter 3. Fluid mechanics. 3. Gauge covariant derivative, field theory, Chapter 7, 8, 10, 11. 4. Covariant derivative and Lie derivative, geometric field theory, Chapter 11 and Book 3. 5. Derivative operator theory in quantum mechanics, Book 4. Adiabatic flow. Adiabatic fluid flow occurs when there is conservation of entropy, e.g., when the entropy per unit mass does not change in time. See equation 3-13. This is usually combined with mass continuity to arrive at an entropy flux continuity equation, when adiabatic flow. See equation 3-14.
Usually the behavior of the entropy density is quite simple, such as constant throughout the fluid, isentropic. Isentropic flow. Isentropic flow is when S equals CO and STANT throughout the fluid. Thermodynamics is the focus of Book 6, but we will make use of minimal thermodynamic relations now to see some nice results. Consider for example the definition of enthalpy W per unit mass when S equals CO and ST period. See equation 3-15. Where V equals 1 over rho is the specific volume, and T is temperature. We can thus write. See equation 3-16. A vector identity that is convenient, here and later when discussing streamlines is. See equation 3-17.
Using this we get. See equation 3-18. 3.1.3 Hydrostatics. Starting with. See equation 3-19. Consider a fluid at rest, V equals 0, thus nabla bullet P equals rho vector G. Since G goes to equals negative G of Z, we simply have P equals negative rho G of Z if the density is constant. If the density isn't constant, then we make use of a thermodynamic relation as with isentropic flow, this time the Gibbs free energy. See equation 3-20.
If we assume constant T. See equation 3-21. Thus, normal phi plus G of Z equals CO and STANT.